let's get to the actual material thing. Okay. So, you'll recall from last time, what were we talking about?
Like at the very end of class.
Well, what was last time all about, aside from the time we spent on homework?
We
were talking about two things. We were talking about the density of what?
Oh yeah, density of the integers, real numbers and irrational numbers. Rational numbers and irrational numbers.
No, the integers and the rationals.
And then the irrationals. They're just.
Well, we'll also do the irrationals. That's just a corollary that falls from the rationals.
Which is still hard to believe, by the way.
Well, we'll prove it. Let's see. Is this 1.1? Or are we at 1.2?
1.2.
1.2, okay. Looking at all that, I'm like, that is not what we did last time. Sorry. Gotta get oriented in my notes. That's the homework for 1.2. Okay, 1.2. So, our first theorem was, let's recap each of the theorems that we went over to make sure we remember them. Our first theorem was what's called the Archimedean Property, or the Archimedean Principle, some people call it. And what was that one?
It just keeps going.
You can always
if
get
you
smaller.
have two integers, then there's always going to be a rational.
For every positive real number, for all C in the positive real numbers,
There exists.
you remember that notation?
Yep.
Comma, there exists a natural number, call it n. There exists n in the natural numbers, such that n is greater than c. So let's make sure we understand this.
Yeah.
Pick any massive positive real number you want.
1,003,022.2.
Doesn't matter how big you picked it, we proved that there is a natural number bigger than that positive number. Right? And then the corollary we got from this right out the door is, for all epsilon, we usually use epsilon to represent a really small positive number. For all really small numbers, there exists a natural number in n such that 1 over n is smaller than that really small number. So in short, what this gives us is any positive number you pick, I can find a bigger positive number, and any small positive number you pick, I can find a smaller positive number. So you can't ever find the smallest positive number, and you can't ever find the biggest positive number. Okay? That makes sense? So those were the first two things we proved. Those were both kind of the same proof. One's just a corollary of the other. The next thing we went over is for all integers. What's an integer?
It's 0 or negative 3, negative.
All positive whole numbers. Not positive, sorry, all whole numbers. So for all integers, remember that z is the set of integers. The interval from a to a plus 1 does not contain an integer. So for picking any integer you want, the interval from that integer to that integer plus 1 does not contain an integer.
Right.
In other words, the interval from 6 to 6 plus 1 is 7 does not contain an integer.
Right.
The interval from negative 32 to negative 31 does not contain an integer. Does that make sense?
Yeah.
Remember that when we use a round brackets, it means not including the ends. So in other words, there's no integer between negative 32 and negative 31. There's no integer between a and a plus 1 if a is an integer.
Right.
Make sense?
Yeah.
Okay. So that was the second thing we proved. The next thing we proved is that if A is a subset of integers bounded from above, A has a max element. Alright, so let's make sure we understand that one. So, if we have some subset of integers bounded from above, then it has a max element. Doesn't every set of numbers have a max element?
No, it has to be bounded.
No, not every set of numbers has a max element, and not every bounded set of numbers has a max element. Look at the interval from 0 to 1. What's the max element in there?
Right. You can't.
Is it 0.999? What about 0.99999? What about 0.99999999999? What's the biggest thing in there? You might come along and say, oh, I know what it is. It's 0.9 like that, right?
Equals 1.
No, that's 1. Sorry, that's not in there. So you can't find some max element in there. Are you skeptical about that? Okay.
You are.
You've probably seen that. Yeah. So this doesn't have a max element. So it doesn't. So not every bounded set has a max element. But we're saying if it's a subset of integers and it's bounded, then it has a max element. Right?
Right.
Why does it have to be bounded? Don't all sets of integers have a max element?
No, we already decided that.
Why do we have to say it has to be bounded from above?
Because there's always an integer bigger.
Yeah, because if it's not bounded from above, this proves already it doesn't have a max element. Pick any element that you think is its max, I can find a natural number which is an integer bigger. Okay? Understand these three?
Yeah.
So you mean bounded like it has to have a bracket?
Bounded from above means it doesn't go on to infinity.
0 to 1 doesn't go on to infinity.
Right, so it's bounded from above and from below.
Yeah, but it
Here's
doesn't
one
have a
that's-
max element.
I know. It has to be a subset of integers.
Oh,
With me now?
yeah.
Okay. Good question. 4. What was the next thing we proved? The next thing we proved was that
If it has a least element, or if it's bounded from below and has a least element, right?
no, that just follows from this, but we didn't need that for where we were going. Next thing we proved is that for all C and R, pick any real number you want, there exists one and only one. That's how you read that symbol. K in Z. There exists only one integer such that K is also in C to C plus 1. Okay, so let's make sure we can make sense of that. I'm saying pick any real number you want. Pick one.
5.
Pi. So we got pi to pi plus 1.
Didn't we already go over all this?
We're saying that this contains an integer in it, and it only contains one integer in it. And what's the integer contained in there?
5.
4.
4. Pi is not an integer.
Oh.
Pick another real number.
3.
Don't pick an integer. Huh?
Square root of 2.
Square root of 2. So let's look at the interval square root of 2 to the square root of 2 plus 1. We're saying that there's one and only one integer in there. And what is it?
2.
1.
2.
Is square root of 2 bigger or smaller than 1?
This is small.
Bigger than 1.
It's bigger than 1.
Let's think about it this way. Is the square root of 2 greater than the square root of 1?
Yes.
So, what's the square root of 1?
1.
1. So square root of 2 is greater than the square root of 1. And it's obviously less than the square root of 2 because,
It's obvious.
or less than 2 because square root of 4 is greater than square root of 2 is 2. So square root of 2 is between 1 and 2.
That's 2.
Make sense?
Mm-hmm.
Okay. So this is some number between 1 and 2. This is some number between 2 and 3.
No, 2 and 1.
2 and 3.
2 and 3, sorry.
Okay. So the integer contains this 2. So we prove picking the real number you want. There exists one and only one integer in that interval. Does that make sense?
Yeah.
Okay. Oh, did we prove that? No, this is what we were going to prove next. So these were the things we proved. This is what we were going to prove next.
Let's do.
And then after that, we were going to prove that the rationals are dense in R, and then that the irrationals are dense in R. So we're going to do that proof, number 4. Sponsor isn't great. Pick a different one. So 1, 2, and 3. That's what we did last time. Now let's pick up number 4, because we spent almost the whole class doing homework. So this is theorem 1.8. We're going to prove that for all C in R, there exists one and only one K in Z, one and only one integer, such that that integer is in the interval C to C plus 1. Good?
Yeah.
Okay, so 1, let C, let C be any positive real number, or any real number, comma, and I'm going to define some set S equal to the set of all integers such that x is less than C plus 1. Okay? Now, I'm going to have to use, okay, quick side note about number 3. If A is a subset of integers bounded from above, what else do we know about A right out the door if it's bounded?
It has to be containing something. It's not empty.
It's not empty. So I think that's actually specified in the theorem. Is if A is a non-empty subset of integers bounded from above, but in order for it to be bounded from above, it has to be non-empty. So I'm going to be obviously using theorems that we've already proved. Particularly, I'm going to use this theorem to prove this theorem. This theorem only applies if this thing is bounded from above, which it only is if it's not empty. So first thing I need to do is show that S is not empty. Highlight of where we're going. I've got S is a set of integers. I'm going to make it bounded from above, making it have a max element, which is going to be the element inside that interval.
Okay.
Okay? So first thing I need to do is show that S is not empty. So let's see.
So you mean you have to say that S contains something? Why can't you just say S is a non-empty set?
I don't know that's a non-empty set. How do I know that if I take all the integers less than C plus 1, that there's something in there? Maybe there are no integers less than C plus 1.
Any sense? That does not make any sense.
Well, this set isn't empty, but how do I know that's not empty?
It's the set containing integers. Such that there's another number. There has to be a number such that there's another number plus 1.
No. I'm saying pick a number, pick any number you want, and I'm defining S to be all the integers less than that number. Maybe you picked a number where there aren't any integers less than that number. How do I know that there's integers less than every number?
Because of that theorem, right?
No, that says greater than. You can only use what you've proved.
So we don't know.
Yeah, I'm just going to show it. Like, it's easy to show using those. So, 2, if C plus 1 is greater than or equal to 0, then negative 1 is in S. Good?
Yeah.
So, I'm going to handle the two cases. C plus 1, you either pick a positive or a negative number. If you picked a non-negative number if you chose C so that C plus 1 is greater than or equal to 0, I'm guaranteed negative 1 is in S.
Right.
I could have said negative 10 is in S. I'm just saying, if this is the case, I know that there's something in there. And then I'm going to say if this is the case, if c plus 1 is less than 0, then I need to show that there's still something in there. So if c plus 1 is less than 0, then there exists n in n, using our good old Archimedean property, such that n is greater than negative c minus 1, which gives us that negative n is less than c plus 1. So make sure you follow that logic for a second. Little dense for one line. So if c plus 1 is less than 0, I need to show that there is still some integer in the set S less than that, right? So I know by the Archimedean property, for any positive number you pick, is this a positive number?
Yeah.
Yeah.
Maybe I should have written it this way. Maybe that helps it jump out more.
Way more.
Okay, sorry. All right. So I know by the Archimedean property that for any positive number you pick, if c plus 1 is negative, negative c plus 1 is positive. We get that straight from our positivity axioms.
Yeah.
Right?
Yeah.
So I know this is a positive number. So for any positive number you pick, there exists an n bigger than that positive number.
Yeah.
Which means, multiply both sides by negative 1,
Flip your sign.
which flips the inequality. We did that proof already.
Right.
You good? Everything up here makes sense?
Now we have all the numbers.
So in other words, we found n in S. That's all we were trying to do up till now, is show that S isn't empty.
Right.
So we said, look, if c plus 1 is greater than or equal to 0, negative 1's in S. If c plus 1 is less than 0, then I can still find a really big negative number less than that number, using the Archimedean.
Number 3 makes sense, but number 2 does not.
If c plus 1 is greater than or equal to 0, and S is a set of all integers less than c plus 1, is negative 1 less than every number greater than or equal to 0?
It has to be.
Oh, okay.
Remember what S is.
S is a set of integers.
So maybe I should put one more implication on here. Sorry, dragging this one out a lot. Which implies that negative n is in S. Probably helps hammer the point home. So if this is the case, negative 1's in S. If this is the case, negative n's in S. In either case, S isn't empty. That's all I was trying to prove so far.
Right.
So S isn't empty, and it's bounded from above,
Right.
is what I needed. How do I know it's bounded from above?
Because it's integers.
How do I know it's bounded from above? How do I know S is bounded from above?
Because
Look at his definition. I mean, yeah.
Look at what's taken go. X is less than. Oh, because x is less than. If x is less than, that means a high z.
What is an upper bound of S?
C plus 1.
C plus 1 by definition. This is a set of all integers less than C plus 1. Is C plus 1 greater than all the integers in that set?
Yeah.
Yes. That's how I define the set. I picked it so that C plus 1 was an upper bound.
Right.
If it wasn't empty. So it's not empty,
It has an upper bound.
and it has an upper bound. So it's a non-empty set bounded from above.
Yeah.
All right. A lot of work to get to this point. So, then what?
then it has a max element.
Then it has a max element.
Which is C plus 1.
Well, we just know it has a max element. Then S has a max element. What should we call the max element?
Y.
You kind of use X's and Y's for real numbers. Have we used K in here yet?
K is.
Oh, K
Yeah.
is what we were going to do anyways. So we'll call it K. So then S has some max element. We'll call it K. Good?
Yeah.
And we know like k is an integer since it's in the set, right?
Yeah.
So, since c plus 1, well, how can I say this?
You shown that c plus 1's in between k and k plus 1.
I'll write out exactly what I have here and then we'll go over the justification. Since c plus 1 is the upper bound, I'm kind of inferring that c isn't an upper bound. Oh, that time we made my contradiction. Okay. So, let me write it out, sorry. I shouldn't be jumping back and forth. Since that, then k is greater than or equal to c, comma, for if k was less than c, then k plus 1 would be less than c plus 1, making k plus 1 the max. Okay. Sorry, let's make this one make sense for a second. So, c plus 1 is my upper bound, right?
Yes.
So I'm going to say that, I'm trying to show that c can't be the upper bound, and so the max element has to be greater than or equal to c.
Right.
Okay? So here's the logic there. I'm saying k has to be greater than or equal to c, because if k wasn't greater than or equal to c, in other words, if k was less than c, then k plus 1 would be less than c plus 1, making k plus 1 the max element. We already said that k is the max element, right?
Right.
We know that an integer plus an integer is an integer. So k plus 1 is an integer. So if k was less than c, then k plus 1 would be less than c plus 1, so k plus 1 would be inside of s, and that would be the max element. You see why that doesn't work? Kind of a lot going on in one line, so let's make sure we get it. We're trying to say k has to be greater than or equal to c. That's the only thing I'm trying to establish here. Okay? So one of two cases. Either k is greater than or equal to c, or it's not. Right?
Right.
If k is not greater than or equal to c, what is it?
It's less than c.
It's less than c. So either this statement's true or this statement's true, right?
Right.
But if k was less than c, then k plus 1 would be less than c plus 1. Right?
Yeah.
Yes.
Which means that k plus 1 is in this set. This is a set of all integers less than c plus 1.
Oh, so that would
So then k plus 1 is less than c plus 1, which means it's in this set.
Uh-huh.
And is k plus 1 bigger than k?
Yeah.
But what's k?
The max
The
element.
max element.
K is the max element. It's the biggest thing in there. I just barely found k plus 1 in there. That doesn't work. So this statement can't be true.
Okay.
So this statement has to be true.
Perfect.
Sorry, it's like a mini proof by way of contradiction in one line.
Right.
And I don't know, I got lazy because this proof already has a few lines. And hopefully you can follow logic. You go with the logic, ask questions, because this is one of the two major theorems this whole section's all about.
This is good.
Good so far?
Mhm.
All right. Mark, let me double check to make sure I hit record on that. I don't remember if I did.
Yeah.
So 7. Therefore, we have c is less than or equal to k is less than c plus 1. Right? We got k is greater than or equal to c in this line.
Right.
How do I know that k is less than c plus 1?
Because it's greater than c or equal to.
Well, why is k less than c plus 1 though? How do I know this side of it?
Okay, because k is the max
Because-
element and c plus 1. Wait, why isn't it equal?
What?
How do I know
Yeah, what do you say?
that k is less than c plus 1?
Because it's in the set C plus 1.
Because it's in the set S. S is the set of every integer less than c plus 1. So I got this side of the inequality. On this line, I proved k is greater than or equal to c, which gives me this side of the inequality.
Yeah.
Putting those two things together, we get to here.
Right.
Right?
Yeah.
Yeah, why can't k be less than or equal to?
Less than or equal to c plus 1?
Yeah. It would still be in the set, would it not, if it was equal?
No. Is c plus 1 in this set if it's an integer? Is c plus 1 less than c plus 1?
No, it's not down
No.
right there.
Okay.
Has nothing to do with bounded. I mean, that set would still be bounded. If I put that there, then it's bounded by c plus 2. But I don't have that there, which means now it's bounded by c plus 1. But S is the set of all integers less than c plus 1. Okay? Maybe just
Okay.
a text at a time. We've got S, the set of all integers less than c plus 1. We showed that thing's not empty. That's what these three lines are all about. It's not empty. So, S is all the integers less than c plus 1 and it's not empty. So it's a non-empty set of integers bounded from above and therefore has a max element, k. So k is less than c plus 1, its max element is less than c plus 1. And then this line was showing that k is greater than or equal to c. How did we know that k is greater than or equal to c? Because either k is greater than or equal to c or k is less than c. If k was less than c, then k plus 1 would be less than c plus 1, making k plus 1 in S.
Right.
Making that bigger than the max element, which it can't be,
Right.
because k is a max element, so k plus 1 can't be. So it's not in the set. So we all get up to this inequality?
Yeah.
Mm-hmm.
Alright, and we can rewrite that exact same equality using different notation. K is in the interval c plus 1. Those are logically equivalent statements.
Yeah.
What is this interval? It's a set of all numbers greater than or equal to c and less than c plus 1. K is a number greater than or equal to c and less than c plus 1. Therefore, k is in that interval. And we're done, right?
Yeah. K's max element.
Read that top statement again. Are we done?
For all C.
No,
we have
because
to
we didn't
prove
prove that
that
there's
they
one and
need-
only one.
Perfect. We need to still prove the unique part. We just proved that there exists an integer in there. Now we need to prove that there can't be more than one integer in there. So you see how we're done with the exist part of the proof? I probably should split this into two proofs. Kind of think about this as two proofs. So we proved that there exists, now I'm going to prove the unique part.
Right.
Okay? 8. Assume by way of contradiction that what?
There exists two.
Perfect, that there's two elements in there.
K and K prime.
K and K prime. Good name choice. So assume by way of contradiction that there exists K prime in C plus 1.
That does not equal K. Where K prime does not equal
where K prime is not equal to K. What's bigger, K or K prime?
K. I don't know.
K prime. Since K is the max,
Alright.
K is greater than K prime. We're using our definition of that. That's the same thing as K minus K prime is greater than
0.
0. Right? That's what we meant for one integer to be greater than the other. So if their difference is greater than 0 as a positive number, is actually the way we said it, then that's true. So that's just using that definition directly. That's back on the lecture on our positivity axioms, if you don't remember that proof. Or that, not proof, but definition. Okay. 10. distance C is less than or equal to K prime, and K is less than C plus 1, comma, K minus K prime is less than C plus 1 minus C. Let's make sure that makes sense for a second. So we kind of got these, maybe make sure this makes sense for a second. How do I know that K prime is greater than or equal to C?
Because C is the lower, it's bound.
Because it's in this interval,
Yeah.
right? K prime's in this interval. Okay, so we've got, draw a picture real quick to help with the intuition. Somewhere over here we've got C, somewhere over here we've got C plus 1, and in between them we have a K prime and a K, right? So what I'm saying is, the fact that this is greater than or equal to that, and this is less than this, means that this distance is smaller than this distance.
Right.
Good with that logic?
Yeah.
So I'm saying, what is this distance? It's C plus 1 minus C. What is this distance? It's K minus K prime. Let me just hammer this home in case that's throwing you off. If I say here's 10 and here's 7, what's the distance between them? 3. 10 minus 7. If this is A and this is B, the distance between A and B is the absolute value of A minus B in general. Good? So does that make sense?
Yeah.
So I'm saying K prime is bigger than or equal to C, and K is less than C plus 1. So the difference between C plus 1 and C is going to be going to be bigger than the difference between K and K prime.
Right.
Good? And rewriting that inequality one more way, we have K minus K prime is less than what?
1.
1! Wonderful. See that?
No.
What's C plus 1 minus C?
Oh,
1. See it? Okay, so I have an integer. Ew, I shouldn't have done it that way. Sorry. You understand this? Let me rewrite this one more way and then I'll do what I'm saying. So I have 0 is less than K minus K prime. I think this will help you see it better. Is less than C plus 1 minus C. So let's make sure we understand this whole inequality in one go. Why is K minus K prime greater than 0?
Because it can't be the same thing.
Because they're not the same number.
I thought we were doing that. That's the K prime.
Oh, we might have already stated that somewhere.
You did.
Yeah.
Oh, we got it right there. Perfect. So just using this, put that piece of the inequality right there. Good.
Yeah.
And then this, put that piece of the inequality right here. Good? Okay. Now I'm going to rewrite this, simplifying the right-hand side.
You can't have 2 integers between 0 and 1.
2 integers. This is only one integer. K minus K prime is only one integer. Why is that bad?
The difference of 2 integers cannot be. It
The
has to be a
difference-
whole number.
There's,
It has to be a whole number.
Isn't K the max?
Okay, this is just an integer.
Okay.
So I found an integer between 0 and 1.
That can't happen.
Why?
So
Because it has to be a whole
there's
number.
There isn't an integer between 0 and 1.
Yeah.
I didn't write that over here, but remember when we were proving this, we first showed that 0 to 1 doesn't contain an integer, and therefore a to a plus 1 does not contain an integer.
Obviously, 0 is an integer and 1 is an integer.
And there's no integers in between them.
Right.
Right. So if this has 2 integers in it, then the difference of those 2 integers is between 0 and 1.
And that can't happen.
And that can't happen.
An integer
How does
minus
that
an
work?
integer is an integer.
Yeah, that was the leap I was going to try to get to make. Why is this only saying one integer is between 0 and 1? Isn't this saying that we have two integers between 0 and 1?
No, saying we have one.
What's that integer?
It's k prime minus k.
It's k minus k prime. Do you guys understand that this is just another way of writing an integer?
Yes.
Right? How many ways can I write the integer 7?
3 plus 2 or 3 plus 4.
Infinite.
Oh,
Here's one way. 7, right?
yeah. Mhm.
So we found some integer, k minus k prime, between 0 and 1, which doesn't work.
Right.
And that finishes the proof. 11, therefore, the statement's true, right? So do we understand all the logic there?
Yeah.
This is a very important little theorem that we just proved. We showed that if you take any interval of 1, where it's open on one end and closed on the other, that's going to contain one and only one integer. We're trying to figure out how often do integers come up on the real number line. So I've got the real number line. Right, here's 0, 1, 2. We kind of mark the integers as we go because it helps us think about it. But if I'm moving along this real number line, I'm kind of wondering, how often do I hit integers?
Right.
And this is saying I'm guaranteed to hit one and only one every time I cover an interval this big.
So let's cover 0.5 to 1.5.
Yeah, I'm guaranteed to have covered at least one integer and to have covered only one integer. See, here's the counterpart to what we're going to prove next. We're going to prove that the rationals are dense in R. What does that mean? So, one way that we could have thought about the integers is, how big of an interval do I have to take to always have at least one integer? How small can I make it and still have at least one integer in there every time?
Right.
Right? That's what we're asking. So if I take an interval that big, obviously I got more than one integer, right? But if I zoom in too much, I didn't get an integer.
Right.
So we can't zoom in as much as we want and still get an integer. So the next question then becomes is, what about for rationals? Is it possible for me to keep zooming in closer and closer and closer so that the only numbers I have are irrational numbers in that interval? Can I make an interval so tiny that the only thing in there are irrational numbers and there's no rationals? Is that possible?
I want to say no. But
Yeah,
you
I'm gonna
say
say
yes.
no too.
He says yes. He says yes for rational and irrational.
Something so small that there's only irrationals.
Yeah, can I get an interval so small so that the only numbers in there are irrational numbers, not rationals? So in other words, if I were to put a dot everywhere that there's a rational number, could I make an interval so tiny it's between two of those dots? Is that possible?
No.
No?
Yeah.
Yeah. Can't I get like 3 irrational numbers in a row? So it goes rational, irrational, 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 rational, and then just pick that interval. You don't think there's ever an interval like that?
No.
None of you do?
I don't think that there's. No, because.
You can always
You
get
can
small
always
or
have-
rational.
Yeah.
Wonderful! That's correct. We're going to show that no matter how teeny of an interval you get, you always capture a rational number in there. That's what we mean by the rationals are dense in the real numbers. They're dense. You can't take some little snippet of the real number, some little piece of the number line, and not have any rationals in there.
And then the same.
They're dense. They're everywhere. You can't get away from them. Every little teeny interval you take, it's got rationals in it.
Irrationals are dense too.
And then the irrationals we're going to prove are also dense.
You can't get
No
so
matter
small.
what small interval you take, you can't get just rationals and you can't get just irrationals. You're going to get both, no matter how teeny of an interval you take.
That's hard.
And that's the two things that we're going to prove next.
Sorry, I feel like cactus, huh?
Yeah.
Tiny limits. Yeah.
So 5 is
What is that again? Rationals is
the rationals are dense in R, or another way that we're going to show that is, given any interval A and B, where A and B are real numbers, remember for this notation to make sense, B has to be greater than A. So given some open interval, there exists some rational such that that rational is in that interval. That makes sense? See how these two ideas are logically equivalent? It's exactly what I was explaining. Here it is in notation now. Any interval you take, doesn't matter how small of an interval you take, doesn't matter what that interval is, I can find a rational number such that that rational number is in that interval. Or another way, in other words, A will be less than Q will be less than B. You can always find a rational number that satisfies that for any interval you pick.
And A and B can be irrational.
A and B are just real numbers. They can be rational, they can be irrational. Okay?
I don't know how we're going to prove this.
Yeah, I mean,
Because we're going.
This one's actually a lot easier to prove than this one.
This is massive scale, that's tiny scale.
I know, and it turns out the massive scale is a lot harder to deal with.
Well, you probably use the massive scale to prove the smaller scale.
Yeah. I'll get rid of all this.
Who was I admiring the other day for how well they could erase a board?
oh my god, boss.
Everyone's got their talents. Some of us can feel them, others of us
Some
can
are
erase them.
so slow. Ariel, what is so slow at erasing a
Yeah,
board?
that's true.
Okay. So, prove that, we're going to prove that Q is write my E before dense in R. That's what we're going to prove. One, I need some open intervals to talk about. So
AB.
one, let A, B
Be real numbers.
be any interval. And remember that means that A and B are real numbers and B is greater than A. That's what that notation means.
Yep.
Good?
Okay.
And I'm going to prove that there's a rational in here. So 2, by the Archimedean property,
Is that the one we just proved? Or is that the bad
No,
one?
the one.
these two are logically equivalent ways of doing it. I'm going to use this. By the Archimedean property,
There exists an absolute.
there exists a natural number such that 1 over n is less than b minus a. Now remember, b minus a is a positive number because b is greater than a. Right? In other words, I'm saying I can find a natural number so small that 1 over n is shorter than this interval.
Right.
So b minus a, that's the length of this interval. And I'm saying I can find a number 1 over n so that that number is smaller than the length of this interval.
Right.
Okay? Because then I'm going to find an integer in a special interval that implies a rational is in that interval. I'll just show you, and then I think walking through it carefully will help. By our last theorem, the one I just erased, which was theorem 1a. Oops, T-H-N. Theorem 1a. That's this guy right here. Good?
Mm-hmm.
Theorem 1a, there exists an integer, I'll call it m this time, such that m is in the interval from n times b minus 1 to n times b. So let's make sure we understand this real quick. There seeing it all in one go. This proof's not that big, so maybe seeing it all in one go will help. And then just rewriting out exactly what this tells me. This tells me that n is between these two numbers, right? This tells me nb minus 1 is less than or equal to m is less than nb. And then all I need to do is divide by n to get my rational. What's a rational? An integer divided by an integer, right? That's a rational. So if n is an integer, then m over n is a rational. So m over n is going to be my rational number that I'm showing you.
So you're getting b minus 1 over n.
Yeah. Then divide this by n. What do I get? b minus 1 over n is less than or equal to
m minus n.
m over n.
Oh, sorry, m over n.
Is less than or equal to b. Now I left a hole there that I'm going to fill in with one more piece of information.
You can add 0.
Oops. I want my hole here. Not 0.
No, you erase the n. Oh, sorry.
What am I trying to show? I'm trying to show that there's a rational in this interval, right?
Yeah.
So what needs to be over here?
Irrational.
I need a. I need a less than that, less than that. How can I justify that?
You didn't get.
I mean, big picture, what you should have been trying to do. If we were to write the first line and the last line, we would have said, let a be this, and then our last line would have been something like, then there exists some rational, m over n,
In integral.
in AB, which is the same thing as A is less than m over n is less than b. So I mean, this is the big picture of what we were trying to get to,
Yeah.
right? Something like that, where m and n are integers. So that's the big picture where we were trying to get. But how does this make sense? How do I know that a is less than bn minus 1?
B.
1 over n, oh,
Doesn't-
sorry,
yeah,
I'm
it's-
combining my things.
Yeah. I was like, why did you change
This is b minus 1 over n. Sorry.
Okay, now
Okay.
it's obvious.
Now it should make more sense.
Yeah. A is the start of the interval, B has to be less than A, and B minus a number, obviously still less than A.
Greater than
How do I know that this is greater than 8?
Oh, why is that?
Because b is greater than a.
Oh, wait, I don't know. Why?
Do a little bit of algebra with this. What do I get? Add a to both sides maybe. A plus 1 over n is less than b.
Subtract 1 minus.
Now subtract 1 over n from both sides.
Yeah.
Good?
Mhm.
Yeah.
But this should have also appealed to your intuition. So we've got our number line. Here's b, here's a. I chose 1 over n so that was less than this distance.
Right.
So 1 over n is only this long. Here's 1 over n. I chose it so it's less than this distance, right?
Yeah.
So 1 over n might be that long. So b minus 1 over n, if I go 1 over n back from b, I didn't go all the way to a. So b minus 1 over n is still greater than a. There's another intuitive way that you could have seen it. But anyway, so that gives it to me, right?
Yeah.
So let's make sure that we understand the whole process like you can do this in general. I give you any two real numbers. You need to find a rational between them. How do you do it? By the Archimedean property, there has to be some n smaller than it, right?
Yeah.
Then I find the integer here. M, that's going to be my numerator.
Okay.
And dividing both sides by n gives me this inequality. I don't know, you getting stuck on something?
You didn't stuck on where you got n.
M?
And
In the B.
N.
nb minus 1. n is in the set or in the interval n b minus.
Okay, so here's what we'll do real quick. So looking at this inequality, you know how to get from this inequality to the inequality of, let's see, a is less than b minus 1 over n.
Okay.
Plus a to both sides minus 1 over n from both sides, and you get this, right? So my goal then is this, which is also less than b, right?
Mm-hmm.
So I took this new interval, which is a smaller part of this interval.
Okay.
I took this new interval to make an interval for integers to get my numerator, and then divided by n again to get back to here. So I took this, multiplied by n, so now we're talking about integers, and then divided by n, so we're talking about rationals again. So
Okay.
that's big pictures, but make sure you understand the logic all the way there. So I picked n so that this inequality is true. Right? No matter what you pick for a and b, I can find an n so that b minus n is in between those two. Good?
Right.
Alright, so once I have that, then multiplying both sides of this by n and creating this interval, I'm guaranteed that this interval has an integer. That's from our last proof.
Where's your an though?
And
Because you said you multiply. Don't you have to multiply?
okay, well, don't skip ahead for a second. Make sure that you understand how we get to here. So from here to here, so I've got this interval, multiply it by n, and that gives me this. And if I include this interval, here's one more thing I could have said. M is in the interval an, or n times a, n times b.
Right.
Okay.
Because n times a is less than nb minus 1. So maybe make two number lines here to see what's happening as we go. So we've got an a, we've got a b, and we've got 1 over n, which is some distance, right? Then we came down here and we found an interval so different number line, we scaled this thing up by multiplying by n, which is most likely going to be a massive number. If 1 over n is really tiny, then n is most likely a massive number, right?
Yeah.
So now we got some massive interval. Here's bn. Here's an. And then bn minus 1 is somewhere over here. I know that a is less than b minus 1 over n, so an is less than bn minus 1. That's multiplying both sides of this by n.
Right.
Okay, so you see how this is kind of what it looks like?
Yeah.
Now I'm saying, if I can find an integer in here, that also gives me an integer in here, and once I have an integer in here, divided by n, that gives me a rational in here. So if I can find an m in here, which is also an m in here, then that means m over n is in here.
Okay, I understand.
So you took something small, blew it up, and then took something small again.
So I took something which is potentially small.
Mm-hmm.
I blew it up so massive that I'm guaranteed there's an integer in there.
Mm-hmm.
I found the integer in there, and then divided by n to get my rational in here.
Oh.
By scaling it back down by the same factor that I blew it up by. Really small, blow it up, find an integer, scale it back down, you have your rational.
Oh.
Does the overall logic of what we did there make sense?
Yeah.
Yeah.
Okay, so that's why we're doing this. We're finding m's in there because that gives us m's in there. And if m's in there, then m over n is obviously in here.
Right.
So that's overall what we were
We
doing.
need to get a rational.
To get a rational in here, we need to find an integer in here.
Right.
Right. So find an integer in here, boom, you got your rational in there. Good?
Yeah.
Okay. So, that is for rationals. Now let's do for irrationals.
How do you even write an irrational?
You just say it's not irrational. That's what it means to be irrational.
Oh, true.
So now we're going to prove that the set of irrationals is also dense in R.
Why is there not a symbol for irrationals?
Well, you can invent one if you want, but we already have a symbol for rational, and irrational just means not rational. It's not common that you talk about just a set of irrational numbers. Talk about a set of rationals all the time, talk about a set of integers all the time, you talk about a set of naturals all the time. It's like saying, why don't we have a symbol for all the numbers that aren't integers? You can invent one if you want, but chances are no one's going to use it because it's just not something you reference that much. Anyways. 1. Let A be any interval. Right? And let z, I can assign z to be any irrational number I want. I'll just do square root of 2 for now. But I could have said let z be any irrational. And the proof still follows the exact same. But we'll start with the square root of 2 to see it in action. Alright. From theorem 1.9, which is the last one we did. From theorem 1.9, comma, there exists x in az bz, where x is rational.
Do we know that
A rational times an irrational is irrational? Yeah.
okay.
3, then x. Oh, I guess I could have done over z. I just doesn't matter which way we do it. I did over z and then multiplied instead of times z and divide. Both sides. A over z, b over z. So then there exists a rational in that interval, which means that x times z is in a b. And we're done. So pick any two real numbers you want, a and b. Right? I'm saying since you can find a rational in a over the square root of 2 to b over the square root of 2, then that rational times the square root of 2, which is irrational, is in here. Right? So in other words, 9/2 times the square root of 2 is irrational. Pick any integer divided by an integer you want, times it by the square root of 2, and it's irrational. Any scalar factor of the square root of 2 is irrational.
That makes sense.
Not
So
scalar
A
factors,
and B
sorry,
have to
sorry.
be integers or any numbers?
No, they're A and B are any numbers. They could have been rational or irrational, doesn't matter. A and B are any two real numbers. All I know is that B is greater than A. But A divided by square root of 2 and B divided by square root of 2 are also real numbers, right? Rational or irrational, who knows? They're real numbers. So this interval contains a rational. That was our last theorem. Pick any two real numbers you want, you get a rational.
Right.
Well, if there's a rational in this interval, then there's an irrational in this interval. Because any rational times the square root of 2 is irrational.
Right.
And I just used d equals the square root of 2 here. I could use square root of 3, I could use pi, I could use any
You did
irrational.
the same thing. You scaled it down. Well, you scaled down, then you scaled down. You scaled down both sides. Didn't you?
No. So I said, you start out with our interval, and I scale it down where we're dividing by I don't know if it scales lower or not. Depends on what the irrational number is. I just rescaled it.
And then undid that scale.
I just rescaled it so that the product of that with my scaling factor was in here. It is the same thing I did over here. It's just in this case I happen to know I'm scaling up. But I just rescaled it to where I could find an integer and then scaled it back to my original thing. I took this, rescaled it to a place where I could find a rational, and then scaled it back so that my scaling factor times the rational I found would be irrational. Okay. So it's really just scale it by some irrational number. And I could have multiplied by z instead and then said x divided by z is in here. Same thing. That's what I was about to write, but it's not what I had in my notes, which means it's probably not the way the author did it. So there we go. Any questions about this?
Yeah, why do we care?
Why do we care?
Don't get into this.
I don't want to know why I care that the irrationals are dense in R.
Dude, that's kind
Well, you could reduce that question to why do you care about any mathematics at all?
So that you're not dense enough.
Because you're not dense about the real numbers.
My question is, like, why do I need to know that? Why can't I just not know that?
Well, here's what I like to think. Imagine that you were to go back in time and talk to some poor farmer who doesn't know how to read. And you're trying to explain to him that there's great value in knowing how to read, right?
Mm-hmm.
And he says, how does reading help my crops grow? How does reading make me a better farmer? How does reading put food in my belly? What do you tell that poor farmer?
It doesn't.
It
How
doesn't.
do you give him this idea that the knowledge that you can get in and of itself is of value? That's going to take a lot of philosophical argument. So I can tell you that there are philosophical arguments that conclude that happiness is based in obtaining virtues, or depending on how you view knowledge, obtaining virtues and knowledge. Mathematics is knowledge to the extent mankind can obtain knowledge. It's the closest thing you can get. So the simple answer is you're a happier person the more you know. Now you know one more thing. Another way that you could view the question is, what are the applications? What are the applications for all this?
Mm-hmm.
There's a story about Euclid teaching one of his students. And Euclid showing him this proof. And his student says, how am I ever going to profit from this? Meaning, how am I ever going to make money from this? Euclid throws him some money. He says, there you go. You made some money. Can we get back to what's important? Which shows, again, the difference in the mentality between people. Simple fact of the matter is, a lot of mathematics that's developed, the instant application for it just isn't known. One of the greatest fields that's an example of this is number theory. Number theory is a field that has been being developed since the ancient Greeks. It's one of the oldest fields of mathematics that there is. And there was no practical application for most of it in the real world until computers came along. Computers come along, and now number theory, it's tremendously useful. All of encryption is based in basic number theory. You can learn how encryption works in basic number theory class. In fact, if we would have gone far enough in discrete math, I think we would have covered it.
We had a choice to do that, or
Oh, we made a choice. So it's so simple that I can teach it in, a couple classes is all you need. So this field was sitting here being developed with no application until way more than 2,000 years after it started being developed. So you have people like Euclid who proved that there's no last prime number, which wasn't a useful applicable fact until over 2,000 years later. So a lot of mathematics that is developed, the application isn't immediate. Now, all the applications with calculus is pretty immediate. Calculus is one of the most applicable classes that you'll ever take because all the physical phenomena in this universe is just differential equations. What that means is, in short, you take any system in our universe, if you know the state of the system and how it's changing, then you can pretty well predict it anywhere into the future and anywhere into the past. Now, there's limitations on what you can physically know that you've been studying in physics class, but it's just tremendously useful like that. But a lot of mathematics, the instant application of it, isn't there. And fields of mathematics that are being developed right now, the application for it, who knows?
Wait, people are still growing mathematics.
Yes. Not only, I mean, there's just tons of things that people are working on proving right now that we don't know about, but not only that, there is this very disturbing proof in mathematics that you can't prove everything. You can't prove everything. Not every mathematical theorem can be proved. So first off, we know there's an infinite number of proofs to be found. And that it is impossible to prove them all. Even worse than it being impossible to prove them all. Like we know that there are theorems out there that our brain just can't comprehend what the theorem would be. Just physical limitations like that. But there's other even more disturbing limitations that no matter what set of axioms you choose to operate on, you can't even just use from those axioms to prove everything. So maybe I can't find all the proofs, but maybe there's some set of assumptions that if I looked at all the theorems that come from these set of assumptions, then they would lead to proving everything. Maybe I can just find the starting point. No, it's actually impossible to find a starting point. You can't even come up with a set of axioms that you can prove all of mathematics from. One of two things is going to happen. Either you get enough axioms that you prove a contradiction, or you don't have enough axioms. You can't prove everything, or you're going to prove a contradiction. So either they're inconsistent, or you can't prove everything. We don't want inconsistent, because then you get a bunch of nonsense. So we're stuck with you can't prove everything. So there is no limitation on the amount of mathematics.
So new proofs are coming out every day.
New proofs are coming out every day, I'm sure, but more than that, there's theorems that have been worked on for over a century now that people are still working on. I mean, one of the ones that's fairly recent in the world of mathematics, I think it proved it in the 90s, is called Fermat's theorem. So this thing, mathematicians were fanatically working on for over 200 years, and you might know Fermat's theorem. Can you find numbers that make that statement true?
Uh-huh.
Yeah, 1, 2, and 3, right? What if I put a square up here? Can you find numbers that make that true? Yeah, 3, 4, and 5. It's just the Pythagorean theorem now, right?
Mm-hmm.
Any right triangle makes a statement true. Okay, so now if I, instead of asking case by case, if I put an n up here instead, and I say my only rule is whatever n you pick, it has to be greater than 2, not greater than or equal to. It has to be greater than 2. Pick any n you want greater than 2. I claim that you will never find 3 numbers that satisfy this equation, as long as n is greater than 2.
Cubed.
Yeah, so if you put 3 in there, you won't find any. If you put 4 in there, you won't find any.
You won't
If you
find
put
any
5 in
ones.
there, you will not find any numbers that satisfy the equation.
That's
What? That
So,
doesn't make any sense.
Let's go back to the case where n's 1.
Okay.
Can we find numbers that satisfy this equation?
Yeah.
Yeah.
2, 3.
1, 2, 3. 1 to the 1 plus 2 to the 1 equals 3 to the 1. Okay, found it.
Okay. And
Sorry,
then I have the-
whole number solutions. I need to specify that. Whole number solutions. Next question is, what about this equation? A squared plus b squared equals c squared. Can you find any whole numbers that satisfy this equation?
3, 4.
Yes. 3 squared plus 4 squared is equal to 5 squared.
Mhm.
Okay, what about cubed? Can you find any numbers that satisfy this?
2.
No, they don't exist. Any whole numbers you find will not satisfy this. And not only will it not work for a cubic, it won't work for the power 4, for the power 5, for the power 6, for the power 10, for the power 8, onwards.
You think it works for an even?
Dude, what the? What?
So this is a relatively simple problem to understand. Right?
Yeah.
Can you find any numbers that make this true where n is greater than 2? That's a real simple problem for you to understand. The proof of this problem is absurdly complex.
Heck.
And so this was a problem. Fermat was a famous mathematician, and he said that this has no integer solutions for n greater than 2, and he put that in the side note of one of his things, and he says, and I have a proof for it, but there's not room in the margin. And he went on his merry way.
But did he really have a proof?
No one knows for sure, but it's highly, 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 highly unlikely that he did. Because the mathematics that had to be developed to prove it didn't exist at the time. So it's most likely that he thought he had a proof, because that happens all the time. Mathematicians think they proved something, then a bunch of peers review it, and they find out, no, you have a mistake here. So he didn't have a peer-reviewed proof. He just had his own proof, made sense to him. Chances are he didn't. But, so there's a simple statement, simple problem. Does this have any solutions? Which it took 200 years to find, over 200 years to finally prove. No, there are no integer solutions for A, B, and C if n is greater than 2. And that's now proven.
Does n have to be an integer as well?
It turns out it can just be irrational. And you can also say A, B, and C are just rational numbers. Because through similar techniques, you could say if you had one for the rationals, you had one for the integers. So,
But not for real numbers.
but not for real numbers in general, no.
You tell me I can find it. Oh.
You can find real numbers that make it true all the time. That's not hard.
What?
Like what? Well, if I say whatever the cubed root of 1 is, plus whatever the cubed root of 1 is, equals the equals whatever.
Yeah, that's it, Donnie, right there. 1, 1, 1, and 1.
Well, oh, sorry, non-trivial solutions. You can't use, no, that still doesn't work.
Cubed is less than 2. So 1/3.
1 plus 1 cubed is equal to,
Oh, square root of 1. Why didn't you do that?
sorry, that doesn't work. Let me think. So I want 2x is equal to y. 2 cubed root of x is equal to the cubed root of y. So pick an x and you should be able to find a y which satisfies that.
Right.
So there's infinitely many solutions to that. Which, any solution to that obviously gives us a solution to this, where x is a and b and y is c.
Right.
So real number solutions isn't near as interesting as integer solutions. Oh, the non-trivial case is 0. Sorry. That's what non-trivial case is. I know that was one. Where a, b, and c aren't all 0. So that's called Fermat's theorem, and there's a theorem that was forever ruled and was only recently proved. So, and yeah, there's tons of even famous questions out there that we're still trying to figure out.
Like what?
One of the most famous ones in computer science is called P versus NP. And what the question reduces to, for your intuition, is it really harder to check a solution than it is to come up with a solution? Are those two fundamentally harder things to do? So let me give you an example. A Sudoku. How long does it take you to solve a Sudoku?
Wow.
A long time. How long does it take to check a Sudoku?
Really fast.
It's really fast. So for some reason, I can check a Sudoku way faster than I can solve a Sudoku. Is that because I'm just really stupid at solving Sudokus and I'm not doing it right? Or is it fundamentally harder to solve a Sudoku than it is to check a Sudoku? So that is a simplified case of P versus NP. P versus NP asks, is it fundamentally harder to solve a Sudoku than it is to check a Sudoku? We don't have a proof that it is. And if it turns out that there is some secret way to play Sudoku that actually makes it just as easy to play Sudoku as it is to check a Sudoku, then a lot of crazy stuff is now possible in computer science. Like, encryption's out the window. Turns out encryption, it's real easy to figure it out. Because encryption is not really based in NP, it's based in factoring. But as soon as quantum computers come out and get bigger and we have to change our security model, then it, well, even with factoring the way that we have it right now, is it really harder to factor a number than it is to multiply the numbers together?
Right, that's a good.
Because right now, encryption is based on the fact that it is really hard for you to find factors of a number. But it's really easy for you to multiply those numbers together.
That would be cool if they figured that out.
So either those problems are fundamentally different, which most people suspect that they are, or they're secretly the same. And right now, that's like the big holy grail question of computer science. But there's tons of other questions out there. I mean, that's just ones that get a lot of publicity. I think they even made a movie based off of those two being the same thing.
Like what would happen? What would happen?
Kind of. It was more just focusing on the mathematicians who did it, and the guy who did it, the computer scientist, mathematician who did it. Did some crazy hacking stuff, but it wasn't a good movie. Sounded like a great premise for a movie. I thought I would be interested in it. I think it's called Traveling Salesman.
Yeah, it seems like anyone with the intellect to think of that premise would understand problems.
Yeah, a lot of movies get you that way. You know, some writer finds out about some actually interesting idea. They think they
But really,
understand it.
it's Donnie telling Jake about it, and Jake goes and makes a movie
Worse than that.
without understanding
The
it.
thing I found out about movies, I don't know how it's found out. The thing that finally occurred to me about movies, only writers write scripts. How many people with an IQ of 140 are writing scripts? What do people with an IQ of over 130 typically do? Math, physics, that's what they do. They don't write scripts for movies. Who's writing scripts for movies? Not the geniuses of the world.
Why you gotta do
They just
it?
need to check their script. They just need to check their logic again.
Well, it
Is that
turns
what
out
they-
it's not even that big of a deal in a lot of things. To have a consistent universe, I'm thinking about movies now, but some guy I watched took the time to actually do surveys and get statistics on this. The majority of your movie viewers do not care about a consistent universe.
Right, honestly.
The majority of your movie viewers
Superhero movies.
do not care about a consistent universe. That's not what we mean by consistent. We mean it doesn't contradict its own premises. So in other words, if in one movie you have Superman lifting up a mountain, and in the next movie he's struggling to lift up a car, that's inconsistent. Car weighs way less than a mountain. If he can lift a mountain, he shouldn't have any trouble with a car. Most people who watch movies don't care about consistency.
That's obvious.
That was not obvious to me. That blew my mind. Because there's nothing that pulls me out of a movie quicker than inconsistencies. It's why I can't enjoy a good horror movie to save my soul. Horror movies are so terrible at this.
Because
The only ones I've actually enjoyed were, oh crap, what are they called?
Beyond Belief? No.
No.
Is it a series of The Conjuring
The
series?
Conjuring series. That's the only one that does a
We
good
legit
job
watched that this weekend.
sticking to their universe. I mean, they're not perfect at it, but holy cow, they do such a better job than any other one I've seen. Because the other one that my wife's big on horror movies for some reason, which is weird because I scare the crap out of her. But It. So I guess the new It came out, so I was going to watch the first It and then watch the second It. And I watched the first It, and this movie makes no sense. It makes absolutely zero sense because you got this weird clown thing, and the premise of the show is
Beat your
there's a secret clown, or I don't know how it came into existence, but this clown that's been in this town since before the founding fathers came along, because you have them in like old photographs, living in a well, I guess, where he was before the well was dug. Who knows? But he likes this well now. So he comes into existence with the well, I guess, and now he lives at this well in this old town.
He's the brother.
And he eats kids, eats little kids,
You guys like
but also somehow feeds on the fear of the kids. So later in the movie, they bring out this premise that he didn't eat a particular kid because the kid wasn't terrified of him. But then earlier in the movie, you see him eating kids where he just like gets the kids to come over to him and acts like he's their friend and then eats them. It's like they were never scared of him. They thought he was their friend, and then he ate them. But then later on in the movie, it's like, I can't eat them if they're not afraid of me. Or I won't eat them if they're not afraid of me, or something like that. And he can't hurt them if they're not afraid of him.
As they get over their fears, they start whacking it. And push
I
him
fell
down
asleep.
even deeper hole.
So it's this crazy clown. He can teleport everywhere. He can do all sorts of crazy things, manipulate them into seeing things which are actually not them just seeing it. It's real, but only they can see it. But it's still real. Like they have to clean up the blood. If you remember the movie.
Yeah.
So all sorts. It makes zero sense. You basically got. It's like if you were to watch Superman get the crap beat out of him by some 10-year-old kid. He's got all these superpowers, but the kids are not afraid of him, so now he's gonna die. Or not die, just get beat up and starve, I guess. I don't know. Weird. It makes no sense. So, consistency issues. Horror movies are terrible at it. You got whatever the scary thing is in the beginning is doing all sorts of things, and there's no way to stop it till it's being stopped by stupid things like whacking it with a stick over and over again. I mean, you would think if it existed for several hundred years, it would be pretty good fighting. No, can't dodge a stick.
It dies because it gets smacked by his.
I don't know if it dies. You just see it crawl back down into like the well inside the well. I don't know what that thing was I crawled down into, and it comes out once every 27 years because hey, 20 is too long. I don't know. So I can't enjoy.
Overcome fear and push him away.
I can't enjoy horror movies for the most part.
Just
The Conjurings try, it feels like to me, to stick to a premise for what can and can't happen in their universe. So a consistent universe is what I like. That's why I don't like the new Star Wars movies. They
Yeah.
ruined the Star Wars universe.
What was that consistent?
What was inconsistent?
In the new Star Wars that came out.
I mean, just the one that's just the most obvious is
Like,
when she uses hyperspeed to destroy an entire fleet. You remember that? The big conclusion of The Last Jedi? Purple hair girl, misgender studies, aims a ship at the fleet, puts it into light speed, and destroys the whole fleet in the process. Here's the problem with this. Is this the first time in the Star Wars universe this has ever been thought of? And is that how is that how light speed works in the universe? It's not that they go into some other dimension and come back out in another location. Is that there are things physically moving through it that fast? Because then if it's physically moving through it that fast, even the little bit of space dust should be destroying their ship. I mean, if you go through a little dust particle at the speed of light, there's a problem there. Right?
I see what you're saying.
And so this could have been a fighting tactic that's used through all this history of fighting going on. But no, this is the first time it's ever thought of. This is the first time it's used. Another consistency issue. She's the general who won't tell her crew what the plan is. She just wants them to follow her blindly. These are the good guys. We're not talking about the Nazis. We're talking about the good guys fighting the Empire. You do as I say, period. Doesn't matter if it makes sense. That's the regime that they're setting up. That's kind of messed up. You have Leia using her magical powers. She's in her ship. It gets blown up. Metal gets torn apart. Leia's body's perfectly intact, floating through space. And then she floats over into the ship, only to die anyways. Good duty. Just let her die then and there. That's when you're going to kill her. Don't make her Mary Poppins her way to the ship and then...
Mary Poppins.
Yeah. So,
Have you seen the second new movie?
the second new movie, you know what? I haven't even gone through The Last Jedi. I have tried on 3 separate occasions to finish that movie.
isn't that the second one?
And I haven't gone through it.
Oh, the last.
I haven't even tried to watch Solo yet.
I heard Solo was good.
You probably heard a lot of bad things through that.
Yeah.
Yeah, there's a problem now
That is
in
the worst
media.
movie critique I've ever read.
Huh?
And in his class is bad at critiquing movies. That's what he said.
Well, now it's, if you critique a movie that has a political agenda, then you're a bad person. Right? If I have a problem with The Last Jedi, it's because I have a problem with women in strong, confident power roles, right?
Well, no
That's
one,
why I have a problem
no
with
one
it.
I ever talked to talks like that.
Yeah, you won't hear that.
Talks like what?
You don't hear that in this town? I've heard it from people I know quite well.
In this, dude.
you'll hear from
People that
two girls
I
in
am
our
related
school.
to.
That what? If you critique.
Oh, if you don't like
Oh.
Blanche, you hate, you're a sexist because you don't
Yep.
like her.
That's the kind of stuff that's getting into movies now.
Yeah, Disney got wrecked by
You
it.
just give them 2 thumbs up, Jake. 1 for each.
And it's just getting into all the movies. Captain Marvel is terrible. Bray is terrible.
You hate Andy.
Hanging was so dumb.
I love Andy.
The first hour of that movie could have been cut out, and it wouldn't have changed anything. You had an hour of them sitting around crying about something that happened 7 years ago.
Yeah, it's a big deal.
Jews didn't complain that much about the Holocaust.
I'm
Good,
sure they're still
Judy.
crying, actually.
7 years ago, a bunch of people died. 7 years ago.
That's a big deal.
Who do you know that died 7 years ago? Could you imagine going and crying about it now?
If half my friends died, yeah. The day
You would still go cry about it.
I'd be like, I gotta remember them.
And the superheroes moving on can't move on with their lives. Everyone's stuck in a rut for 7 years. You can't move on.
What bothers me so much is that the Earth went to shit. Like they didn't go and like do their job.
Like Thanos wanted them to do.
Like all of a sudden they were just bumps.
Yeah, and the whole premise of that movie is retarded. Everyone knows what population growth looks like. If you get rid of half the population from here to here, you know how long it takes back to get to there? A year! When did the Earth have 3.5 billion people on it?
Probably like 30 years ago.
Well, probably more than that. I don't know exactly when it was, but probably close to like the 1950s. Did he set back population 50 years? Oh my goodness. It'll really save those resources now.
Yeah, but how Americans think they stop having babies?
What?
Americans stop having babies, so
Bruh.
maybe it'll take them less.
Well, that's a consequence of advanced. I mean, that's not an American thing. That's a standard cultural thing. So as your rate of infant deaths dies off, then the number of children that people have decreases, and that's been noticed across all cultures.
Do
Not
you think
just
our population is going the fastest it's ever grown?
growing as fast as it's ever growing. Yes, because population growth is both related to
Deaths and births.
how many people there are and birth rate. So just because you have a way lower birth rate now than you did 1,000 years ago, doesn't mean the population is growing slower.
There's just
Right.
a lot more people.
And so what happens with population growth is it usually looks like this and then tapers off at some max. When you see it in nature. Because typically you can't have too many bunnies, otherwise the grass won't grow.
Right.
But if you got some bunnies, then they reproduce like bunnies.
Right.
Until they're eating all the grass that there is to eat.
Right.
Till the death rate and the birth rate are roughly the same.
Is that ever gonna happen here?
With human population, it's a much harder thing to speculate on because of how much control we have of our environment. Humans are the one species that they don't live now the same way they did 5,000 years ago. If I were to go take you and stick you 5,000 years ago, you dead.
Same.
If I go take someone from 5,000 years ago, stick them here, they'll live thanks to like social programs, but they're well out of their element, right? You live far, far different. But a lion now lives the same way a lion did 5,000 years ago. So we aren't like all other animals in that we don't live the same way that we always did. We drastically changed the way that we live. So there are some people that have all sorts of upper bound estimates on it. Some as low as 9 billion is, I think the lowest one I've seen is what someone estimated.
That's the dumbest
Earth's
thing.
population will, 9 billion is upper bound for it.
Dude, we saw.
And other projections I've seen have been way higher, like 20 billion. So I've seen a bunch of different projections. I've honestly never personally looked into everything that they're basing that off of to come out completely about it. Because you also have, the possibility, we're just able to make things so much more efficient. With 1 acre of ground, we can grow way more food than we could with 1 acre of ground 200 years ago, thanks to genetic engineering. I can get crops to produce at maximums and all sorts of things. So physical resources aren't as much of a limit on us as they have been in the past. The greatest example of that is, I don't remember exactly what the numbers are, but there's something like the year 1900, is it 1900 or 1800? One of those two, then it was over 90% of the American population was in agriculture,
Right.
growing crops.
Nothing's like.
Nowadays, I don't even think you go to nowadays, I think if you go to the year 2000, then it was less than 10%.
Right. That's bad.
So assuming that we're not importing a lot of food, you had 90% of the population had to grow the food for everyone. Now we can reduce that job to 10% of the population.
That
so they
same
can grow
thing
the
is
food.
going to happen to every robot's developed.
AI,
Yeah.
it will. You'll see it happen with a lot of things, not everything. So genetic engineering is going to be a way bigger factor on crop growth than AI. AI is first going to infiltrate things that
Security.
you don't need something physical for. So one example of a company out there, what their AI is really good at doing is getting rid of middle management. So they can't get rid of the employees, but they can get rid of all the middle management. So we have the AI, it looks at all the processes that are going on for a bunch of companies.
Shows you where to put your crap resources.
It watches how middle management people do their job, learns from how they're doing their job, comes to conclusions about how they should have done it versus how they did do it. And then you can outsource that part of your job to this piece of software now, have that do everything that your middle manager was doing.
Is that
As
just
opposed to
right?
have, yeah, there's companies, I can't remember the name
It's
of the company.
busy a middleman company.
Busy can allow you to remove middle management. Busy itself, we don't have middle management at the company, but we're.
I'm talking about using busy on my excavation company.
Right, so imagine that you were a construction company 100 years ago. How hard of a job is it to accurately track people's hours, who was actually on the job, who got injured, who didn't?
Alright. Well,
Whatever all that information was, and how many people had to do it for how many people. Was it one for every 10 people or whatever it was, or was it actually a thing? But assuming you had one person for every 10 people that did that, that's kind of a middle management job, and now busy eliminates the need for that person. So that's an example of doing it, but that's not how this other company was working. They just specifically developed not the software, but an actual, not a program like Busy, where you use the program instead of the job, but an actual AI, which would use other software that it needed to actually replace the middle manager. Does that make sense what I'm trying to say? Yeah, so
that's
that kind of stuff can be taken over by AI rather easily. So if there's no physical aspect to it, and it's just coming to conclusions based off of data that you see, the AI is really good at that. Because it can analyze way more data than you could ever hope to,
way more.
and it can come to way better conclusions about it than you could ever hope to. It's
That's
just
why I should get
insanely good at it.
Programming.
Well, I should
AI.
get into AI.
It's one of the things I'm doing right now is working on a side AI project.
With
Should
Jared.
we put our stocks into it?
Jared is working on it, but the guy who did it is a guy by the name of Craig. And his big premise is to make AI work more like life. Think more like living organisms work. So his degrees are in computer science, mathematics, and then chemistry or biology?
Biology, you're telling me biology.
I think it's biology. Anyways, he knows a lot about how biology actually works, and so he wants to make an AI that, to the best of his ability, mimics exactly the way that life works. Now, life and the way life works and the way easy math works is not close to the same thing. So right now, all the AIs are over on the side of what makes the math nice. He wants to do it of what's the closest to biology, and then just figure out the math the best you can.
Do you think it has a future?
Well, I wouldn't be involved in it if I didn't think that it has somewhat of a future. He talks about it like it's the next big thing since the internet. I'm not near as hopeful as he is, but if even 1% of what he says comes about, then I will be very happy with what happened. And it's also just a fun thing to work on, to have a project to get involved in AI in general. But I don't have But yeah, to the best of my ability that I've been able to find, no one's doing it how we're doing it, so it's different than everyone else is doing it. Maybe it's better, we'll find out if it's better.
You could be a millionaire.
Yeah.
What I'm saying is, if this thing was the next internet, you could be a Steve Wozniak.
Well, I have no desire to manage a company that does it. I just want to work for the
Well,
company
Steve
that does it.
Wozniak was a manager.
Well, I have no desire to own a company and be responsible for that kind of money.
It's not hard to buy stocks.
Huh?
So it's not hard to buy stocks.
Oh, yeah, if the company ever took off, own shares of the company, sure. Now, I just can't imagine a funner job than developing an AI for a living. Like, if I could just focus on developing an AI and not have to worry about anything else, that's as good as programming gets. Programming is already a ton of fun.
Blast to develop.
Huh?
AlphaGo. I watched a
Hey,
documentary
I
on
watched
the
that one.
development.
Oh,
Looks like a blast.
yeah, I can't imagine a funner job. Like, that's just how you're going to spend your time, from sunrise to sunset. How do you read that?
Did you see how he won one round? How he did a move that the computer has never seen before?
Are we
Yeah.
on track or are we behind?
We're behind.
Humans 1-1.
For like today?
We've been behind since the beginning. It took 2 weeks to get through the preliminaries.
I know, but I'm saying.
Let's go ahead and go on break, and then when you come back, I'll
Don, do you watch
That's what
stocks
we're
at all?
watch what?
Stocks, like public stocks?
No.
Not particularly, no.
That we've-
Kinda did a while back.
investing.
We're just doing
Don's game.
our stocks today. And I'm wondering if there's a hot stock.
I don't know of a hot stock,
Don't buy Funko.
but could
What should we do, Mark?
Actually, I do buy Funko.
create a really simple AI and let the AI decide which one to do.
Look at this. We're down from 27 to 1950 in a month, less than a month.
That's what you've been in.
So I imagine it'll pop back up soon.
You're actually serious about Funko?
I've got over $1,000.
Have you made a lot of money off of it?
All time, I've made $87 in my investing career.
Dude, Don has made thousands of his.
But I've lost hundreds of dollars
So-
in Funko recently.
I'm going to tell you the same thing I told Lawrence.
I'm down.
It is real easy with the stocks to delude yourself into thinking you made an intelligent choice and you didn't gamble. You're gambling. You're playing with the stocks. Let's make this very clear.
Dude, I totally
Gambling.
do not want to be a stock player.
Well, it's
No,
going to be a stock.
Not because if I'm playing stocks, it's for entertainment.
Yeah. Don't delude yourself into thinking you're making these great decisions because. So there is one mathematician who finally decided, I'm going to use math to make money. And he did. He made billions. And what did he do? He started a company that manages a mutual fund, and he started hiring mathematicians. And they would develop AIs to predict what the stock market's going to do. And that's what they would do for their mutual fund. And the company's still going now. They take ridiculously large cuts of your earnings. I think they take 35% of what they make you.
Really?
What it costs.
That shit still makes people a lot of money.
Oh, I'm sure it does, because it's still in business. But listening to him interview about how much harder it is to make accurate predictions about what the stock market's going to do, there's an interview with him where he talks about how insane this is getting. To be able to make accurate predictions, to have an AI able to do that, and an AI is going to do so much more than you could ever hope to do.
I'll bet you the more AIs you throw into the picture, the more complicated stocks get.
Right, the more reactive they are, the harder they are to predict.
So the minute you're getting things right, the stocks
Yeah,
get
that's
right.
where Jared, Jared's kind of the one that had the idea. That's where he is hoping to make money off of our AI. So the big advantage to our AI, it has a lot of downsides, but its one big advantage is you can train it fast. You can train it so much faster than other AIs. And that's the big holdup on AIs right now, is how long does it take to train them to do something? Training them is when you have them look at all the data and be able to come to good conclusions based off of the data. So that's what our AI would have the big advantage in, is the training time is way faster And so the application he sees for that is we'd be able to do analysis on data from stock prices to purchase, what are they called?
I know what you're thinking about.
The things that makes like you can have guaranteed you can purchase stock for this amount of time. Options. There we go. So he wants to be able to train our AI based off of the stock prices that are coming out that day to develop on how to pick options. Because if our AI works the way that should work, we should be the only one able to train that fast. And so we should have a huge advantage in that arena.
That'd be cool.
So that's the way he wants to put it
That's
into
exciting.
practice now. We'll see what happens, but it's a cool place to test it.
Oh, I had a lot to talk about too. Donnie, remember when you came and taught our 9th grade class, or our 7th grade class?
No.
For Esther?
Oh, vaguely.
Yeah.
I'm the physics teacher.
Okay, Donnie, I have a question about Stephen Hawking.
Okay.
What was he trying to do? Like, what was his work? Because didn't he?
Is he dead?
Yes.
Didn't he die a few years ago? Or
He
yes.
died like last year.
Last year.
Because when he was in college, to get his PhD, didn't he have a theory or something that because of a time-space singularity or something that time had a beginning, but didn't he go and prove that the universe is infinite and there's no time or something like that?
So you're talking about misconceptions about the Big Bang in general. I mean, Stephen Hawking's most famous work is what we call Hawking radiation, which is the idea that black holes radiate, which means that even black holes will eventually dissipate and lose their energy. But as far as the Big Bang goes, so you familiar with the Doppler effect?
Like to.
Car drives past you.
Have you ever heard a car drive past you? Have you ever been standing outside and a car drives past you? What does that sound like?
Yeah.
As it's coming at you, it's high pitch.
Mm-hmm.
And as it's driving away, it's low pitch.
That's weird.
He's never realized that.
Well, and the reason is your ears, you understand, I don't know where I could begin.
Kinematics.
You're good with the idea of a wave
Mm-hmm.
and a sound wave, and the idea that when I speak, the reason you hear me is because sound waves are going from my mouth into your ears.
Mm-hmm.
Okay, and then the frequency of a wave, this is a high frequency wave, compared to this would be a low frequency wave.
Mm-hmm.
Okay? So high frequency wave is how many times it goes, it oscillates per second. So this one's not oscillating very much per second. If you think about this axis is time.
Mm-hmm.
So if this is 1 second, it's oscillated once, whereas this one oscillated several times.
Mm-hmm.
So, high frequency sound sounds high pitch, right?
Mm-hmm.
So this is much higher than this is. And these waves look like this, and these waves look like this.
Okay.
So as a car is driving towards you, and this just kind of helps your intuition, imagine that it's emitting its sound wave, right?
Mm-hmm.
So if the car is right here, and it starts emitting a sound wave, okay? But as it's emitting the sound wave, it's also driving forward, which crunches up the wave.
Okay.
Whereas when the car is driving away from you, and now it's shooting the sound wave that way, it's spreading out the wave.
Okay.
So when it's driving towards you and you hear the sound of it driving, it's and when it's driving away from you, it's
Mm-hmm.
And that's the reason. That's called the Doppler effect.
Okay.
So moving objects, I mean, in theory, you could be standing here blindfolded, and you could listen to a car driving by, and you could determine how fast it was moving.
Mm-hmm.
Just by the sound of what it's giving off, right? How much that frequency changes between when it's coming at you, when it's driving away, you can then determine how fast that car was going. That would be possible for you to do, assuming you had the right equipment to do it, right? You could accurately measure those sound waves and all that. So, the same way that sound does this, light does this. Light is also a wave, just like sound waves are a wave. And so it has certain frequencies. And what color of light you see is dictated by the frequency of that light. So, blue light is much more high frequency, and red light is much more low frequency.
Okay.
So in other words, if it were possible for me to have some light source right here that was shining blue light at you, in theory it's possible for me to throw it that way fast enough that now it looks red. creating a Doppler effect.
Okay.
Do you see what I'm saying?
Yeah.
The same way that I could, doesn't matter how high pitched someone's talking to you, if I could throw them away from you fast enough, sounds like they have a deep voice.
That's cool.
Okay.
Similar concept. You with me?
Mm-hmm.
Okay, so that's Doppler. So, a guy by the name of Edwin Hubble, when he was out looking through a telescope at the universe, at an observatory, I think it was in Hawaii. The last thing, I won't get into it very much, but we can also, based off of looking at a star, determine what its chemical makeup is and what color of light it should be giving off.
Mm-hmm.
Okay, so the big breakthrough of Edwin Hubble was, when he was looking at all the stars out there, he noticed that they were all a little bit red-shifted.
Right.
For the most part. For the most part, all the stars that he looked at were a little bit red-shifted, which was weird. And he noticed that the further away a star was, the more red-shifted it looked.
Okay.
So the conclusion there was, for some reason, everything in space is moving away from us.
Right.
Mm-hmm.
And the further away it is from us, the faster away from us it's moving.
Weird.
Kind of strange.
Yeah.
That's weird.
So there's kind of two ways that you could instantly interpret that. The Greeks are right. The Earth's at the center of the universe, and everything's moving away from us. That's one way you can think about it. Or you can think about everything in the universe is moving away from everything in the universe. We lean on the second one rather than the first one. And the way you think about it, or the way I like to give you intuition to think about it is, well,
Points on the balloons.
yeah, points on a balloon, but make one more point maybe. Think about how weird that is if everything in the universe is moving away from everything in the universe. Doesn't that kind of imply that there's like empty universe that doesn't have anything in it yet, and now stuff can move and spread into it?
Yeah.
Yeah.
See, that's not what's actually happening, or that's not what we guess is happening. Because if everything's moving away from everything, then that means that space itself is increasing. So it's not really that you and I are moving away from each other, but that the space between us is growing somehow.
That would be cool.
Okay.
Well, that's what's happening, according to our findings. So that's what's happening. It's not that stars are just moving away from each other and some reason speeding up the further away they get. It's just that stars, the space between stars is expanding. And that's what we mean by the universe is expanding. Right now, at this very second, the universe is expanding.
That's like
The space between everything is constantly getting bigger and bigger and bigger for some reason.
Okay.
And here's the intuition on how I like to help people think about it. Imagine you had a balloon,
Okay.
and I put a bunch of dots on the balloon.
Mm-hmm.
And then I start blowing up the balloon.
Yeah.
Those dots move apart.
Yeah.
How? Are the dots moving?
No.
No!
balloon
The amount of balloon between them is growing.
Right.
Right. So that's the intuition for what's happening in our universe, is that
We know that pop.
that's
and we'll all come back.
that's what's happening, and that space in between objects is actually
One of those
growing.
balloons.
More space is growing. The universe is expanding. And so if the universe is expanding, then it must have been smaller in the past.
Balloon in the cartoon.
Right?
Yeah.
Right.
If these two dots are this far away now, well, that means they should have been this far away ago 1,000 years ago, and this far away ago 1 billion years ago, and this far away ago 5 billion years ago, etc., 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 until they came from the same point.
What the heck?
So all the mass in this universe came from the same point.
Okay.
That's why we believe in
Look at billions of
And that's the idea of the Big
One
Bang.
in my mouth and you're
The idea of the Big Bang Theory is that all the mass in this universe came from a single point and expanded out from that point.
What the heck? Okay.
So that was the idea of the Big
That
Bang.
means time started.
Remember when you
Now, there's a lot of ways that there's a lot of speculation you can make about that. One of the speculations you can make is, before the Big Bang, what was?
Time.
There was no time, there was no space. So Einstein's model of space-time is a four-dimensional manifold called a space-time. Wow, what are the odds? Space-time's called space-time. And when we use his idea of general relativity to run the numbers backwards, and yeah, everything goes back to this one singularity, and then it kind of breaks down. And so a common interpretation of it is the beginning of space and time is that instant of the Big Bang. So the question what happened before the Big Bang doesn't make sense. Nothing. There was nothing.
Before implies time.
See, people have a hard time with the idea of nothing. What is nothing?
Before.
The absence
It's what
of
you
something.
see behind your head.
Is it big empty space? Is that nothing? No, that's big empty
That's big
space.
empty space.
What's nothing?
The absence of something.
I love Aristotle's description of nothing. It's what rocks dream about. Nothing. That's what nothing is. It's what rocks dream about. Nothing. That's what nothing is.
I still have a hard time wrapping my head around that.
Well,
Everyone has
it's
that.
hard. It's not intuitively there.
One of the ways I
What color do you see behind your head? Nothing.
yeah, so this is actually an interesting side note. Interview with a blind person. People were asking him some questions, and one of the questions that they asked is, what was like the biggest surprise about going blind? So it was a person who had their sight and went blind. And so they were asking questions about the difference. And then one of the main things that they focused on was, or one of the biggest differences he was trying to communicate to the crowd was, he's like, I want to tell you, it doesn't go dark. It doesn't go black. You don't see. I don't see blackness. I don't see.
That's not true.
What the heck?
That is not true.
I
People-
don't see black, I see
It's
nothing.
not that I see blackness, it's that I don't see.
Holy cow.
It's like, what does your elbow smell right now?
What?
What do your eyes see
I
right
would
now?
freak out. That actually is scary.
You don't see, like,
You don't see. You're blind.
yeah, but
You don't see black. It doesn't look like this. You
Your
don't
brain's
see.
not interpreting blackness over and over again and
then what
communicating
is it
blackness.
interpreting?
It's
What's behind your head? What do you see behind
Not,
your head?
holy what?
That's what
There
he
is
sees all
no
over.
way.
No.
yeah, so that's a good thought experiment to help you think about what nothing is.
What
What's
nothing looks
nothing?
You
I just
can't.
like Gandalf in his white.
And they've actually found out, I mean, the way that your brain helps handle this is your visual cortex, part of your brain that's very much associated with seeing things, it retrains itself to do a lot of stuff based off of hearing. So they get really good at, based off of sounds alone, I guess, reconstructing in their brain a map of the universe that they're in.
Yeah, apparently.
Because you do that all the time,
What the heck?
based off of all your senses.
I tell people I'd way rather be blind
Then what?
than
Death.
That's just stupid.
no.
Good grief, you're messed up.
Human interaction, music, my two priorities.
Useless. If you're blind.
Not useless, there's a bunch of things that they've used to
Yeah.
make that.
Alexa.
Could you imagine trying to learn this blind? You can't read.
You're right. I couldn't learn that. I could give bread to.
Huh?
And I could learn this. I could get bread to.
Yeah, you could have someone read it to you, but how often do you have to look at the visual of something to help you figure out what's going on?
Right.
All the
But
time.
I'm missing voices, which I cannot let go, and music.
How about you just don't be
I'm
guided?
missing human interaction. Like I would never get human.
Just turn on the subwoofer and feel the music.
No.
Dude, you're way more lost at what people are feeling if you can't see them than if you can't hear them.
I disagree.
How well,
You're
they
standing
say
in a
how
group
much
of
of
people.
communication is nonverbal communication? Well, when you find out everything that they start classifying as nonverbal, then it's just
Dumb.
yeah, or communication breaks down too. Anyways,
Okay, let's do this. Dog, in the syllabus, we were supposed to cover 2 sections today,
yeah,
and we've only covered 1.
yeah.
Okay, let's cover the second one.
Second section is not that big. All right, second section is working up to what is called the triangle inequality. We're going to do a couple quick lemmas before we do the triangle inequality, but in short, it's ways of dealing with absolute values and inequalities. Absolute values and inequalities are going to come up all the time in calculus. We want some basic theorems that we can use to deal with these things. So, first off, what is absolute value? What's the definition of the absolute value function? The absolute value of x is x if x is greater than or equal to 0, and it's negative x if x is less than 0. So what's the absolute value of 3? Well, 3 is greater than or equal to 0, so it's just 3. What's the absolute value of negative 3? Well, negative 3 is less than 0, so it's negative 3, or 3. Definition make sense?
Yeah.
Okay, so let's move on to some basic lemmas, and then we'll do the triangle inequality. So first lemma we're going to handle is that the absolute value less than or sorry, C and D are real numbers. D is a positive real number. Okay? The absolute value of C being less than or equal to D is logically equivalent to negative D is less than or equal to C is less than or equal to D. Okay, that's what we're going to prove.
Okay.
So in other words, if the absolute value of negative 3 is less than or equal to 4, that means negative 4 is less than or equal to negative 3 is less than or equal to 4. If the absolute value of 3 is less than or equal to 4, that means negative 4 is less than or equal to 3 is less than or equal to 4.
Okay.
Good? So let's prove it. So if and only if, so we're going to show this implies this, and then this implies this. We're going to go that way first. So let C and D be real numbers, such that our condition, remember, assume your condition, show your conclusion. Right? So assume I have two numbers, C and D, such that this is true, where D is greater than 0. With me so far?
Yeah.
Alright? So now we've got two cases. Either C is greater than or equal to 0, or C is less than 0. Right? So I've got absolute value of C is less than or equal to D. I need to show this being true means this is true. And I need to handle two cases. I need to handle if C is greater than or equal to 0 and show it's true. And I need to handle if C is less than 0 and show it's true. You understand the two cases?
Mm-hmm.
Alright, so let's handle the first case. If C is greater than or equal to 0, what's the absolute value of C?
It's less than or equal
It's
to
going to
D.
be the absolute value of C.
What is the absolute value of C? If I plug C into this function, what do I get out?
A positive number.
I get C out. The absolute value of C is C if C is greater than or equal to 0.
Right.
C is greater than or equal to 0, so the absolute value of C is just C. What's the absolute value of 3? It's just 3.
Right.
So if C is greater than or equal to 0, the absolute value of C is just C. So the absolute value of C less than or equal to D is the same thing as C is less than or equal to D. The absolute value of C is C.
Yeah.
Mm-hmm.
Good?
Yeah.
And then if C is less than or equal to D, 0 is less than or equal to C is less than or equal to D. Because I already know that C is greater than or equal to 0. So take this inequality and tack it on right there. C is greater than or equal to 0. We're just tacking that onto this. Good?
Okay.
Mm-hmm.
And then obviously, if D is a positive number, negative D is a negative number. So negative D is less than 0. So if 0 is less than or equal to C, negative D is less than or equal to C. You follow that logic?
Yeah.
Good? Alright, let's handle the next case. C is less than 0. So if C is less than 0, then the absolute value of C is less than or equal to D means negative C is less than or equal to D. What's the absolute value of C if C is less than 0? The absolute value of C if C is less than 0 is negative C. So negative C, so the absolute value of C less than or equal to D is the same thing as negative C less than or equal to D.
Right.
Good with that?
Mm-hmm.
Alright? Once again, we know that C is less than 0, so we know that negative C is greater than or equal to 0. You see how this part of the inequality follows from this?
Yeah.
Good? So we've got this whole equation so far. Finally tack on to negative D. Negative D is going to be less than or equal to 0. So we just replace the 0 with the negative D, because that's an even smaller number. Obviously. You get up to here?
Mm-hmm.
And then multiply here by negative 1, flips the signs. So D is greater than or equal to C is greater than or equal to negative D.
Which is the same thing as that.
Which is the exact same thing as this. So we showed in both cases, if the absolute value of C is less than or equal to D, then D is greater than or equal to C is greater than or equal to negative D. Good?
Yeah.
Alright, now let's show it the other way. Let's assume that we have two numbers C and D such that negative D is less than or equal to C is less than or equal to D, where D is a positive number. Good? We're going to break it up into our two cases just like before. We're going to handle the case where c is greater than or equal to 0, and we're going to handle the case where c is less than 0. So if c is greater than or equal to 0, and we already know that c is less than or equal to d, so I'm just going to use that part of the inequality. Just to help you see ahead, I use this part of the inequality for this case and this part of the inequality for this case.
Okay.
Anyways, so if c is greater than or equal to 0, because c has to be one of those two things, less than 0, greater than or equal to 0. If c is greater than or equal to 0, then this part of the inequality, c less than or equal to d, just means the absolute value of c is less than or equal to d. Because if c is greater than or equal to 0, what is the absolute value of c? It's just c. We can interchange those. Good?
Yeah.
So just take that part of the inequality, make that an absolute value, we're done. With that case. So we showed that if this is true, then this is true for this case. Now when you show if this is true, then this is true for this case. Let's move on to the next one. If c is less than 0, start with the second half of this inequality that we assumed. Negative d is less than or equal to c is the same thing as multiply both sides by -1, flip the sign. D is greater than or equal to negative c. You go with here to here?
Yeah.
Alright, and then what is negative? Oh, I'm just going to flip my inequality around. Here to here, I didn't do anything. I just changed the order.
Yeah.
Good with that?
Yeah.
Yeah.
To help you see it. And then here, what is the absolute value of c? It's negative c. So negative c, absolute value of c, same thing. And I just switch that out. If c is less than 0, what is the absolute value of c? Negative c.
Okay.
Negative c, absolute value of c, absolute value of c, negative c, same thing.
Okay.
Good with that?
Yeah.
Okay. Next little lemma. Negative the absolute value of x is less than or equal to x is less than or equal to the absolute value of x.
What? Okay, yeah.
Yeah, pick any number you want. Let's make sure it makes sense. -3. What's the absolute value of -3?
-3.
-3. No.
Well, negative absolute value.
-3.
Right.
I didn't say what's negative the absolute value of -3. I said what's the absolute value of -3?
3.
3. So -3 is what this whole thing is. Is less than or equal to -3 is less than or equal to 3.
Yeah.
One of these two is always, it's either going to be equal to this or equal to this.
Right.
And then between the two. Alright, so let's handle the two cases to prove this. We're going to handle the case where x is greater than or equal to 0 and the case where x is less than 0. Common cases when you're
These are
handling
easy.
absolute value. So if x is greater than or equal to 0, then we know that negative x is less than or equal to x, right? If x is greater than or equal to 0, then this is a negative number, this is a positive number, or they're both 0, right? And the negative is always less than or equal to a positive. So you good with going from here to here?
Mm-hmm.
And then that is obviously true. X is less than or equal to x. That's always true, because it's always equal, right?
Mm-hmm.
Now, what's the absolute value of x in this case? If x is greater than or equal to 0, what's the absolute value of x?
X.
It's just x. So I can take all my x's and swap them out with absolute value of x if I want. So I'll take that x, swap it with absolute value of x, take that x, swap it with absolute value of x, we're done. Good?
Yeah.
Alright, next case. If x is less than 0, then we're going to have x is less than or equal to negative x, right?
Right.
Because now this is positive and this is negative.
Right.
If x is a negative number, then negative x is a positive number.
Okay.
Positive greater than or equal to negative. And then this part of the inequality, once again, is obvious. Right?
They're equal to each
So
other.
this is the only part that you need to make sure you understand. Then you get the whole thing. Perfect. Now let's see. Oh, one more trick. X can be rewritten as negative x. Right? That to there is all I did from here to here. You go with that?
Yeah.
And now what's the absolute value of x in this case?
Negative x.
Negative x. So I can swap out my negative x's with absolute value of x. So that negative x, absolute value of x. That negative x, absolute value of x. And once again, we proved it.
Yep.
Good?
Yeah. Why don't you let us do those proofs for our homework?
Do them. There you go. Along with your homework, you're now required to do these two proofs. Courtesies of Jacob.
Easy.
Oh, by the way, give me your homework. Make sure you turn that in to me. So do that real quick while I write up this proof for the triangle.
Or you want to show me that?
Yeah, just on my desk is fine. You better all have it, seeing how I did it all in the last
Well,
lecture.
Julie, you can go copy every product from our class.
I can't copy because that's cheating. And after that one, my last
We group thought it, okay?
You
Okay, so for those of you that were in my geometry class, we proved this in geometry, triangle inequality. Came up geometrically, now it's going to come up algebraically. Very useful little theorem that comes up over and over again. But make sure you understand it all. We're saying the absolute value of the sum of any two numbers is less than or equal to the absolute value, the sum of the absolute values.
Okay.
So pick any two numbers you want in there real quick. Let's pick 4 and negative 3. What's 4 plus negative 3?
1.
1. So the absolute value of 1 is?
1.
So over here we get 1. What's the absolute value of 4?
4.
What's the absolute value of negative 3?
3.
What's 4 plus 3?
7.
Is 1 less than or equal to 7?
Yes.
Okay, so there's an example of it in action.
Okay.
A case where it would be equal, just pick 0 for everything. Or pick
Or
positive numbers for
positive
everything.
numbers.
Or just
They're in
negative
the
numbers
same
for everything.
direction.
Same sign numbers. And it will be equals. Different sign numbers, it will be less than.
Right.
That's what it's going to turn in. Anyways, so let's prove this real quick. 1 from, I guess it's 1, 7,
Which one are we referring to?
which is one of those. I'll show which one in a second. Negative absolute value of A is less than or equal to A is less than or equal to absolute value of A, and negative absolute value of B is less than or equal to B is less than or equal to absolute value of B. So that's obviously this one, right? Good?
Mm-hmm.
Now combining these two, I'm going to add these two together, that's why I wrote it that way.
You can add inequalities.
Then, negative absolute value of A minus absolute value of B is less than or equal to A plus B is less than or equal to absolute value of A plus absolute value of B. Good with that?
Mm-hmm.
Yeah.
Okay. I can't believe how many times I did that. And then, using our other theorem, then absolute value of A plus B. Maybe I'll rewrite this one more way to make sure it stands out clear in your mind. Negative absolute value of A plus absolute value of B. So maybe that will help the leap that we're going to take. Using this theorem. Okay, so let's go over it real quick. Make sure you understand it all. Put a little square here. Proved it. So you understand these two are using that Doppler theorem, right?
Mm-hmm.
And then adding these two things together gives us this, gives us this. Good?
Yeah.
And then this theorem says the negative of this, we're using this here. D is absolute value of A plus absolute value of B. C is A plus B.
Right.
So I have negative D is less than or equal to A plus B, negative absolute value of A plus absolute value of B is less than or equal to A plus B is less than or equal to absolute value of A plus absolute value of B, right? So that means that this is true. That the absolute value of A plus B, that thing in the middle, is less than or equal to whatever that D was. So my D was this.
Oh, I see it. Yep.
And so the absolute value of whatever was in the middle is less than or equal to whatever the D was. You see it? It's real simple with these two things. This is actually the most complex way I've seen this done, using two lemmas. And he didn't even bother proving these lemmas, I don't think. He just said, obviously this is true and this is true, and combining the two together, you get this. I think it's like that, I don't remember. Anyways, so that's the triangle inequality. It's going to come up again and again and again.
Can you do that? Can you do that the same with negative? Oh no, you can't. Subtraction is said.
When you put a negative sign in there
Yeah. You can.
and there, that
Well,
changes
unless
it
you change the
drastically.
sign.
If I make that negative and that negative, it doesn't work. In fact, you'd have to flip that.
Yeah, but then it would, right?
But then it would. Because putting a negative in there doesn't change anything.
Mm-hmm.
A plus B absolute value could be the same thing as A minus B absolute value, because those could be positive or negative numbers. But then when you put the negative in there, that's the same thing as what you have over here. Right?
Mm-hmm.
Which we already have up there. Okay. So,
We still have a lot to cover.
we don't really have a lot to cover.
Yeah, look.
After this, he just gives you formulas to get you comfortable with notation. There's no more proofs in there.
Oh, yeah.
So, I think I'll just let you guys go through those on your own, and then you can start the homework. They're formulas that you've already seen before. We'll recap them again in case you haven't at the beginning of next time. Or if you need help with them tonight, I'll be here after school. But yeah, after that, it's just really simple formulas. Let me write one up real quick that you might not be familiar with, and that is this one. It's the n choose k notation.
Oh.
Have you seen this before? I know James has seen it.
I've seen that before.
Do you understand what factorials are?
Yeah.
Anyone not understand factorials? You'll laugh, but it's a common thing people don't understand. So I think you'll understand everything in here. You already know sigma notation. We've been using it. That's what it goes over. I'll do some basic proofs
Do you want the homework problem?
of some of the things next time. But yeah, so that's the end of chapter 1. We'll start chapter 2 next time with some quick review of that. We got way off topic today talking about all sorts of stuff.
Which is just fine.
My mind is blown.
So,
Yeah,
Busy
I
about that blank.
literally broke
Yeah.
well,
I can't wrap my head around it.
well, there. Focus on your calculus and how blind people see.
110